All right, welcome in everybody. We're gonna get started with our next breakout now. We are gonna have Scott Hotaling. He's presenting on rock glaciers and the future water in the Wasatch. What does the future hold? So let's give him your full attention. Thank you.
So it's really nice to be here. I was supposed to present here 2 years ago, but then I got COVID right beforehand. And then I couldn't be here last year. So this is actually my first Watershed Symposium that I've ever actually gotten to attend. And I also had no idea how big these breakout sessions would be. So it's incredibly cool to see all of you and to get to talk about rock glaciers with you. I'm a bit of a rock glacier evangelist, as anyone that knows me will attest to. Before I get into it, I want to thank both the supporters of our work, so Utah State University, the USDA, the Southwest Climate Adaptation Science Center, Snowbird, and then the Utah DNR and the Division of Water Resources. And then when I say our, I'm referring to myself and Matthew Morris, who is a project geologist at the Utah Geological Survey and is very much my partner in crime when it comes to rock glacier work. And I'll actually stand over here so I'm not standing in front of people. So I run the Climate Change in Mountains Lab at Utah State University, and what that means is we study how mountains are changing. Being in Utah is an extraordinary place for this work, although I joke that I'm a bit of a professional bummer outer because the story is usually not positive. But we study all sorts of different things from, like I have a PhD in ecology, but in order to understand what's happening in mountain systems, you can't just be an ecologist, especially if you're working on streams. You have to be also a physical scientist and a hydrologist and kind of integrate multiple disciplines. So we do things like, this is us at Delta Lake in Grand Teton National Park. We're actually coring the sediment of the lake. So we're on the ice surface, gives us a stable platform. And here we're pulling up a 1.5 meter core of sediment. And my PhD student, Anna, is looking at the different layers of that sediment and how potential pollutants are melting out of the glacier, feeding the lake. So things like DDT that have been banned for a long time, but are still stored in the ice potentially. And then we do stuff like I get out a lot in the summer and late spring looking for snow algae. So if you've ever been in the mountains and have seen like a big pink area of the snow, that is actually a green algal bloom producing a red pigment, which I get that's confusing. But that red pigment can actually, it darkens the snowpack and it acts like a dust on snow event and can accelerate snow melt pretty dramatically. So we're working to understand the extent of snow algal blooms, what controls their patterning in terms of nutrients, and if they are getting worse. There's a really wonderful article that was published in the Atlantic like 7 years ago, and the title is "Why the Last Snow on Earth Will Be Red," and it's all about snow algae and kind of this like negative feedback loop of they melt the environment that they are living in. It's kind of like the Great Salt Lake and snowpack and lake effect snow. And just because this is in the news and I think it's really fun to chat about, we also do stuff like we got into measuring mountains recently. And so in Washington State, 100 years ago, there used to be 5 mountains that had ice as their highest point. So that even in late summer, they had perennial ice. And we showed that Mount Rainier is actually 20 feet shorter than anyone says it is, including the national park, and which they are not thrilled about it, but it's the reality. And it's because the ice dome on the summit of the mountain has been shrinking down. And we did a climate analysis to go with it and showed that this totally corresponds with days above freezing on the summit of Mount Rainier. And that's relevant for Utah and anywhere, because what it tells me is that there is no place in the lower 48 states where there isn't direct climate impacts happening right now. Even the tallest, coldest mountain at a high latitude is experiencing these changes. So it's certainly happening in the Wasatch and elsewhere. But mostly, we spend a lot of our time just messing around in streams in pretty directed ways. So here we're looking for bugs. So we work on a bunch of endangered aquatic insects that live in high elevation streams. We do flow measurements, we collect water for geochemistry, and the power of what we do is not that we do some really cutting edge science, although some of it certainly is, but it's that we go to places that very few people are actually looking at. These are hard places to study and hard places to do this work, yet the headwaters of wherever you live, I mean, we literally live downstream of these environments. And so when we talk about what happens at a water treatment plant down the canyon, which that was a great overview of that, a lot of that starts at these little meltwater streams at the source. And so some of that in the Wasatch looks like this. So this is me and Matthew, I guess 2 summers ago. We're installing a little thing called a pressure transducer. This is below a rock glacier this is above White Pine Lake in Little Cottonwood Canyon. And this, paired with going up there and getting individual flow measurements, is letting us start to reconstruct how much water actually comes out of the rock glacier feature and what that means for the downstream environment. We can relate that to things like geochemistry and other potential water quality concerns, etc. And you'll see we have a lot of videos. And I just want to point out that we think it's really, really important to communicate our science beyond academic audiences. I've loved so far in this symposium that a lot of people are talking about the importance of sharing the information and getting people, involved or able to learn more about it. And so we have a YouTube channel called Mountain Futures, and we publish videos about the work that we're actually doing, so you can see what it looks like to do, rock glacier hydrology work in Little Cottonwood Canyon. We also interview other mountain scientists about sometimes really just kind of wild things they're doing that are really intriguing, and other times about really important topics like what it's gonna mean as snowpack declines in the Western US. And so if you please check it out, my students kind of religiously monitor the subscriber count, which is really, really fun. And they send me texts whenever it gets to big round numbers. But also, if you are doing something really cool, we want to use it as a platform to also highlight other people and the work they're doing. So I would love to come join you or send one of my students out and we could make a video together. So it can be a collaborative space as well. And so to understand the future of the Wasatch and how our water resources might be impacted by what's going on, we need to have a bit of a primer on what's been happening so far. And so the first kind of top line thing to know is that no matter what analysis you use, whether MESO West, I use the Climate Toolbox, whatever data you pull, you will see a very standard common trend. Utah is warming. And so the annual mean temperature in Utah over the last 45 years is about 1.8 degrees of warming. And that might not sound like much, but we'll talk about why that's pretty important in a bit. But overall, we've seen some of our warmest years have been in the last couple of years. And what's especially concerning to me as a mountain scientist and someone who just thinks about the overall long-term health of the state of Utah and the Wasatch and mountain communities in the West is that our mountains are warming faster than the lowlands. And so this is a really great analysis done by some of my colleagues at Utah State University. I was not involved with this, but I think it's a really excellent study where they just looked at climate trends at Utah's ski areas, because those are representative of our mountains, and we often have really good data in our ski areas about what's happening. And they showed that on average, we're seeing about a 0.08 degrees centigrade warming per year at our ski areas. And just to do the various conversion math of, they're using the mean minimum temperature, I was using the average in the last slide. So just to put it all together for you, that's about 2 to 3 times faster than the state as a whole. And if you're in a trivia contest about mountain, climate change or mountain research, that phenomenon is called elevation dependent warming. And it's really interesting and important because what it means is as you go up a mountain in the same place, the rate of warming isn't happening linearly. It's more of a hockey stick. And so the rate of warming, it's still colder higher up the mountain, but the rate of warming relative to the position is happening faster higher up. And so if you're a state or a city that gets most of your water from seasonal snowpack, and that it relies on skiing and snowpack for outdoor recreation and all these other kind of benefits that come from it, that's a massive problem because the warming is happening the fastest where you want it to happen the least for things like your water supply and local economy. Of course, warming down in the city has other socioeconomic implications. And so the basic reason for, or the basic implication of this warming and this overall is that we're seeing less snow and more rain. So if you're like me, if you're a backcountry skier or you just like to think about water and the Wasatch, you probably have some of your favorite snow telemetry sites that you like to go look at and see how much is on there. Right now it's really bad. Don't go look at it if you don't want to be a little bummed out. But this is every snow telemetry site in the state of Utah over the 45-year record of when the first one was installed in 1979. And so you can see, I haven't updated this figure, but you can see the historic winter of 2022, 2023 on the far right. The other couple of years you can add and the analysis is the same. But what we've seen is about a 16% decline in the peak amount of snowpack that we have each year. And that's snow water equivalent, not depth of snow, over this period. And it's a steady, slow march downhill, downward. And so when I first showed that slide a couple of years ago, one of the first questions I got was, well, I hear in the news that precipitation patterns are changing. Is this just that it's not raining or not snowing as much as it used to? And there's a really nice analysis that hasn't been published, the update, but it still holds the same trend. They went back 60 years at just long-term precipitation patterns in Utah from the Utah Climate Center. And they showed that actually precipitation statewide has slightly increased over the last 60 years. The difference is this ratio. So snow, S to P, snow to overall precipitation. And what is different is now more of our precipitation is falling as rain, whereas it used to fall as snow. So that 2-degree difference, you can think about if it's 33 degrees outside instead of 31, now you have a very different scenario where you're not getting snow that's adding to our kind of natural reservoir in the mountains. Instead, it's falling as rain, running off immediately, and potentially taking other snow with it, because that rain on the snow can melt the snow and also can drive flooding concerns. Rain on snow events, in May could be a really big problem for flooding and hazards in Utah. And all of this has been termed by scientists like me, although they did an excellent modeling study that's a bit beyond what I could have done, a low to no snow future. And I know that sounds really grim, and it is, but what they're meaning here is not that it won't snow anymore, but that we will eventually start seeing a transformation in how our snowpack builds up. And we'll see these years where we have essentially 10% of our normal snow water equivalent or lower. And basically what will happen is there'll be a snowstorm and there'll be a meltout period. Snowstorm, meltout. And we'll have kind of that up and down oscillation. Instead of snowpack builds up, we have massive reservoir of water in the mountains that then stays for a long time and melts out when we need it the most in summer. And so that will obviously have massive implications for water storage and other things. And so a lot of what I think about in my job is what will we wish we had done in terms of water conservation or economic bolstering or thinking about where people live and other issues before we get a year like that. And if you're someone who looks at this and you're kind of like, well, it's modeling looking out, they're saying this will start to occur around 2060, so in 35 years. And you're like, well, that's a long way away. Like, I don't really know that that's, I don't really buy that. I will echo Ben's comment earlier that the biggest problem scientists have is that they're too conservative what they say. They're actually not very alarmist. I would be surprised we don't have a year like that before 2060. I know these authors and they were trying to be really conservative with how they were approaching this question. It's very robust, but they were certainly trying to make sure that they were not going to be alarmists about it. But if you don't believe that this could happen, I will have you look at southwestern Utah last year. And this is one of the SNOTEL sites I like to check down there. And this was February 13th, when we were in fully uncharted water of how much snow builds up at that site. There was a late season, March-ish storm system that came through and brought them out of being the worst snow year ever there to being one of the worst snow years ever. But you could also look at Europe in 2023 and find all the headlines about essentially how Europe's lack of snow was previewing winter in a warming world, and essentially all the economic and hydrologic and other issues that were coming from a lack of snowpack countrywide. So to me, it's not a question of if, it's a question of when, and what do we collectively do about it. And so this is not a mistake. I'm just going to set up this video. This is all pretty grim. And so one of the parts of all this that is at least somewhat hopeful for me and that I like talking about because there are elements that are better than I expected are rock glaciers. And just a show of hands, before you walked into this talk, how many people had ever heard of a rock glacier? See, that's amazing, because I've talked about them before and no one knew about them. So I feel like I can at least take a little bit of credit for that. When I talked about, well, I'll just play the video first. So I don't have a great one for the Wasatch. This is a video from Idaho, but this is the Meadow Lake Rock Glacier. The reason I want from the Wasatch is I don't fly my drone unless it's 1, legal, and 2, no one else is around. And that's hard to find sometimes in the Wasatch. But there's no one here. And so this is a rock glacier. And what you're seeing is a bunch of furrows and ridges on this kind of lobe of rock that looks like it's flowing downhill. And it looks like that because it is flowing downhill. All glaciers, whether rock glaciers or the surface ice you might see in the Teton Range, they're all just frozen rivers. They're just water moving downhill really slowly. And there's all these little ridges and things that are all the little areas where the ice is flowing differently. And they have these really steep fronts that build up because the ice is actually pushing them forward. And so that's actually called it's steeper than the angle of repose. It's steeper than what would happen naturally without a force actually behind it. And all of the rock glaciers, or a lot of the rock glaciers, have outlet streams and lakes. And so that becomes really important when thinking about their role in both bolstering water supply, but there's also potentially water quality concerns and things that might come with having more and more of our water supply coming from these features. And so when I explained what a rock glacier was to the Division of Water in Utah a couple years ago, they were incredibly receptive. Some of you actually might have been there. I explained what it was, this massive ice in the mountains covered by debris, and kind of why they might be important. And I asked how many rock glaciers would have to be in Utah for the Division of Water to be, for them to be interested in them. And the highest number that anyone gave was 25. And so I am happy to, I set that up poorly. There are 800 in the state. That's a different slide. And so if you want to learn more about them than just that little clip, or you want to see something, we had a really nice NPR piece on All Things Considered last year about rock glaciers and why they're some of the most climate-resistant ice is hiding in plain sight. It's fun because I get a lot of folks that meet me, hear what I do, and then say, oh, I know about this NPR thing, I want to send it to you. And they realize the rock glacier world is very small, quickly. So go check that out. We also, part of my role at Utah State is working with USU Extension. You may know Extension from backyard gardening and things. I'm actually USU Extension's climate adaptation specialist for the state, which if you want to talk about being in a state that doesn't believe in climate change or whatever, you should know that your land grant hired someone specifically to work on climate change. So that is excellent and is a really nice mark of progress and moving forward. So there's also, we wrote a whole bunch about rock glaciers in there, and then we also have a video that basically gives you the rundown of what a rock glacier is with a bunch of different photos and videos of them. But this was the slide that I thought was next. So there are 800 rock glaciers in Utah. They are mostly in the Uintas, especially on north-facing slopes in the Uintas, but there are plenty in the Wasatch and places that you know and love. They look like this. So this is the Mount Timpanogos rock glacier. People call it the Temp Glacier. It is a glacier, but it is a rock glacier, not a surface ice glacier, which is really important for thinking about the future of these features. And it's rare, but every once in a while we get little glimpses of the actual ice inside of them. We see these little exposures. So this is a crevasse that opens up on the Temp rock glacier pretty consistently about, I think it's right around there. And then this is a spot on the White Pine Rock Glacier from a few years ago that a friend of mine was up there and saw this little crevice, this little crack down in where you could actually see meters and meters of ice. And so you can start to imagine if there are, this thing is 2 to 3 kilometers long. It has, we think, something on the order of 20 to 30 feet of ice in it. That's a lot of stored potential water and other things in the mountains. And it feeds this little tarn late in the season where all of what's going into that little pond is coming from the rock glacier. And like White Pine Lake, or the White Pine Rock Glacier feeding White Pine Lake, the water coming out of the rock glacier is about 0.5 degree Celsius. And so it's a really important aspect of the cold water that protects our fisheries and other downstream ecosystems. But also it's the only water going into that reservoir in late season. So I think when you go to, if you find a stream that's flowing late in the year in the Wasatch, the odds are pretty good there's some kind of rock glacier influence higher up it. And so this map I'll just apologize for in advance. It is sideways. That is north over there. So to orient you, I thought it was better to have more space on the slide. I'm not sure that was the right choice, but there are about 100 rock glaciers in the Weber River, BCC, Little Cottonwood, American Fork, kind of that area. So just to give you some context. And so when I started working on rock glaciers and becoming their evangelist in probably 2013 or 2014, I set up a study in the Teton Range, so where I was a graduate student at the time. I wish I'd set up in the Wasatch, it would have been more convenient for my long-term career path, but it's nice to be close. And so we're still doing this, but we have this long-term study in the Teton Range where we go to the same 12 high alpine streams every year, and we collect data on them. And 5 of those streams are fed by rock glaciers, 3 are fed by surface glaciers, and 4 have some kind of groundwater other influence. And we set that up because we had this basic premise that rock glaciers are big masses of ice, they're covered by rocks, and that rock should be a net insulator, and they should actually be more resistant to climate warming than their surface ice counterparts. And so I've been saying that, that's how it should work for 10 years now. And there's been one little bit of evidence from Europe, from a single rock glacier with 70 years of data that was pretty stable over time, that suggested that's true. But nothing from the US and nothing at kind of a larger scale. So it's really exciting to be able to share data from the Tetons, which certainly is applicable to the Wasatch, where for the first time we actually know this is happening. And so I've been working with folks at Colorado State to use LiDAR data, so laser guided surveying, where you can get centimeter level accuracy of a landscape from a plane. And so Grand Teton National Park back in 2014 took advantage of a program to fly LiDAR over the entire park. So the entire mountain range has LiDAR data, has a reference point in time, in September when all the seasonal snow was minimized. And then a few years ago, the USGS did a much larger LiDAR survey of the Western US, which included Grand Teton National Park again. So we have 2 points in time, 8 years apart, where we have really, really robust data. And what we can do is we can look across all that area, and we can first say, is the bedrock the same elevation as it was 8 years ago as our control? And then we can take every single bit of ice in the park and ask how it has changed. Both the glaciers, the named glaciers in the park, and the rock glaciers. There are 11 glaciers in the park. When I say that, I mean surface ice. And there are about 75 rock glaciers. And so I'll show you the results of this. You probably won't need much help interpreting them, but the scale is change in elevation in meters for a given point in space. So vertically up would be blue, red is down. And these are going to be the 11 named glaciers in Grand Teton National Park. So that's what's happening to them. It is not a great story. It is on the order of meters and meters of elevation loss. So I mean, the ceiling here is what, about 3 meters? So multiple stories of ice loss on some of these features. And so then we can put that next to some examples of rock glaciers in the same areas, same basins, same elevations, and look at how they're changing. And again, you don't need much help just looking at that and saying, that is a much darker shade of red than that is. And even these are some kind of old outlines. We've refined these a bit by just going out and kind of ground truthing them. And some of these actually darker red areas on our rock glacier outlines are actually surface perennial snowfields that are in a cirque next to a rock glacier. So they're responding like their other surface counterparts. So that tells us that the debris cover itself is really critical for the future of these things. And we didn't need to quantify that to prove our point, but we did. And so the rate of change for those rock glaciers, about 75 of them, is essentially nothing over that 8-year period. Whereas the glaciers are losing about 0.7 meters of ice every single year. So I'm like 1.8 meters tall, so that's mid-thigh of ice loss. And some of these places I have been to many times over the last decade, and you can walk on the glacier, and where you used to be able to step off a rock knob onto ice, now that rock knob, you would want a rope to climb up to it. And so it's a massive kind of steady loss of ice. And so what it tells me is, one, I mean, I'm naturally bummed out about that, but thinking about how water storage is shifting on the planet. So this is happening all over the world. And so it's not just snowpack, it's also things like glaciers, but a huge amount of water has now been exported downstream and is no longer stored in those mountain reservoirs, essentially, that can then melt out in summer when there's a heat wave or whatever, and keep, we're seeing more and more headlines about fisheries being closed because the water temperature is too high. Cold water sources, meltwater, snowpack, ice, etc., is one of the ways we keep our streams cooler. And so what it also says is this is not a sustainable trend in terms of the glaciers are not going to persist that much longer, whereas the rock glaciers will. And while we don't have any surface glaciers in Utah, we have a huge amount of snowpack. And the snowpack is obviously also dwindling. So you can imagine a world where the Wasatch will be increasingly dominated in late summer by runoff coming from rock glaciers. And so what is their future? How are they going to be affected? Obviously, it's not going to last forever. What water quality implications are there, et cetera, are the kinds of things that we think a lot about. And so we're working, I don't have data for you yet, but we're working to understand if these same patterns are true for the Wasatch. So if you've ever been to Snowbird Ski Area, I'm betting many of you have, if you ever skied on the Little Cloud Lift in Gad Valley, you have been within feet of a rock, probably have skied on the rock glacier. So this is the Gad Valley Rock Glacier that Snowbird is a wonderful collaborator and partner in allowing us to access to this place. We can drive really close to it, which is great for having heavy equipment and other kinds of sensors. But this is the Gad Valley Rock Glacier, and for the last few years, the Utah Geological Survey and Matthew Morris and those folks have been doing repeat LiDAR scans of this rock glacier. And we're basically developing the same type of data set for how is it changing year over year. And what I can show you is that there's definitely ice in it. And we know there's ice in it because it's still moving. And so the upper accumulation zone of it, the higher elevation part, is moving about 40 to 50 centimeters per year. And so there's definitely an active ice body in it. And we haven't actually done any year over year vertical comparisons yet. And so we're doing a bunch of other things as well, because we're kind of holistically trying to understand where should we be spending more or less of our time to better understand these things. So this is a little clip of us at White Pine Lake. We have hourly temperature sensors, so we're collecting data to see how the water temperature changes over time, or if it does at all. My student Anna is working on geochemistry of rock glaciers around the western US, including tons of work in the Wasatch, to understand, like, we know that rock glaciers tend to have a lot of nitrates coming out of them. And if you know much about water chemistry or, algal blooms and things, nitrates going into a lake, if that lake warms up or gets a lot more sun or something, can lead to harmful algal blooms. There's been a little bit of data that has suggested there's been an increase in harmful algal blooms across the western US in high elevation lakes with no real clear reason for it. I wonder if stuff like greater influence of subterranean ice paired with warmer temperatures might be driving it. And then we've also, we use these samplers, so we have these water samples we put out, and they collect a water sample at every predetermined times every day. And so we can actually track water chemistry over a whole melt season, because obviously when there's tons of snowpack going downhill, that's a very different water chemistry signal versus September when it's only the rock glacier melt. And so these are perfect little cylinders, so as someone who likes videos and other things, I naturally put wildlife cameras on them, because we also want to know what kind of species are actually using rock glaciers. We did a study on Mount Rainier, we put some wildlife cameras out, and in one season with 6 cameras, we captured photos of the first wolverine family in the southern Cascades of Washington in over 100 years. And so, again, putting just the little sliver that we actually know about our mountains is so small. And so I think of it as another one of our biotic frontiers, like the tree canopy in the deep sea. But here's, in Gad Valley, this big bull moose likes to hang around the rock glacier. I didn't put any sound in it because I wasn't sure if that would work in this room, but he's like making this great grunting and other noises as he bashes around. We've seen a tremendous number of owls on our cameras, which I think is really interesting. I don't really know what exactly they're doing up there in such high numbers, but we see a lot of owls around. And then our cutest visitor to the rock glacier is this little pine marten. So we got a bunch of videos of them running around last summer. And so what have we learned? We have learned that rock glaciers are likely critical to the future of the water supply in the Wasatch. We don't know exactly what role they are playing just yet, but as snowpack declines, if we have a stable source of ice in the mountains, it's going to be an increasingly larger influence just naturally. And so understanding how they're changing, where they are, other aspects about them is really important to thinking about the future of not only places close to them, but also like the Great Salt Lake and other downstream places. They are surprisingly resilient to climate warming, which is you don't get a lot of wins when you study climate change in mountains. And so the fact that they are persisting and seem relatively stable makes me pretty happy. But it is not some kind of silver bullet solution. I want to be really careful with this. This does not mean that we don't need to worry about water conservation or whatever because we have all this ice stored in the mountains. I have no idea how the ice in the Wasatch is being affected. We're working on ways to image it, but we should still be doing everything else. But if this perhaps could buffer some of our water supply, that's a great thing. We might already be tapping into it. And so there could be the kind of issue where we think we're not losing as much stream flow as we should be, and maybe this is backfilling in a way that will snap back to reality or something. The jury is still very much out. And then echoing kind of some of the earlier talks, especially the one in this room about long-term climate data, it's amazing as a scientist how valuable long-term data are to actually tell you about what's happening in the world, and then how unbelievably difficult it is to find funding for it. Like it's this conundrum where, the National Science Foundation, when it was functional, they would want you to here's $1 million, spend it in 4 years, do something really groundbreaking, and then kind of that's it. And it's like, well, if you give me $40,000 a year, I could do something really groundbreaking for 40 years. And so we need long-term data to draw robust conclusions, and we need the kind of just basic data from around the mountains, just like those air temperature sensors around the Great Salt Lake. We need this kind of robust network of data to inform what's happening. I didn't put it in here, but we do have a new initiative at Utah State. I've started this endowment called the Mountain Futures Fund, and the whole point is to support mountain research in Utah long-term. And just stuff like going out and installing a temperature sensor. It costs one technician and an $80 sensor. But if you want to contribute something like that, please let me know. It'll all go through USU, not me, because I don't want to handle money. So we need that long-term data. We also need to communicate beyond typical channels. So it's really wonderful to be here. This is a really important part of my job. And I'm happy to talk more to you, or if you have an organization or something where it'd be fun to have where I could serve a role, please let me know. I basically say yes to every invitation, which might get me in trouble eventually. And so I'll leave you with this little video of the rock glacier in White Pine Lake and all the information to find me. This is one of the streams we spend most of our time at in the summer. And it's coming out of, now you hopefully are rock glacier experts, and that is the front of the rock glacier up there. So thank you.
Thank you, Scott. We have time for questions. Just as a reminder, please raise your hand, even if it takes a bit to get to you.
Right here.
Yeah.
Just as a complete rock glacier newbie.
Yeah. I love it.
Can a rock glacier form from a surface ice glacier, or is the mechanisms that create them entirely different?
They often don't form from the surface glacier, but they form in the same places where a surface glacier was, because surface glaciers are there because there's a lot of snow and usually some kind of shielding in terms of the cirque or something like that. But the most critical thing for a rock glacier is where they form, and I should have talked about how they form, is that you need to have a place with a ton of snow and ideally avalanches coming onto something and kind of depositing it. Then you also need some kind of rock fall. And so the Temp rock glacier is great because there's this huge cirque of rock falling down onto it kind of continuously. You can stand up there on the ridge and just listen to it. And so that kind of combination of huge amounts of snow with somewhat crumbly rock is the recipe. And so they become kind of like layer cakes over time, where it's like big snowfall, ice layer, rockfall event on top insulates it. Another one, rockfall, another one, rockfall. And then it gets kind of mixed up as it goes downhill. Yeah, thank you. Yeah.
I had a question about the precipitation trends and the rain versus snow. One of the things I've wondered for a long time is with more rain in the winter, you don't have the evaporation as much.
Yeah.
And it's falling in places with really fractured geology.
Yeah.
Is the kind of other side of the story that we're getting maybe more groundwater infiltration and storage that way? And then the other thing is that, again, since there's not as much evaporation, is that water being transmitted downstream and kind of like quote unquote more efficiently because there's less evaporation? So is it just kind of changing the hydrograph as far as that goes?
It definitely is. Beyond like the actual where it's flowing in the groundwater and how much we can store and where it's going beyond that, I think those are still pretty open questions. There was a really nice study from folks at the U earlier this year talking about groundwater in the Wasatch and the dynamics of it. I'm happy to share that with anyone, but I don't want to overspeak to what's happening since I'm not as sure about that right now.
Could you talk a little bit about how dynamic the rock glaciers are and potentially compared to kind of regular glaciers in terms of, accumulation zone, ablation zone, where some normal glaciers are very, very dynamic. There's a lot of water coming out of them every year.
Yeah.
From your talk, it seems like rock glaciers are a lot less dynamic, and kind of the thought is like, is the ice, how old is ice in here? Is this ice, from, the end of the last glacial maximum type period, and it's just being stored because of that insulation?
Yeah, so that's a great question. And I know that you know a lot about rock glaciers too, because I recognize your name. So I'm happy you're here. And essentially, yeah, rock glaciers in general are much less dynamic in terms of total volumes of water export, total volumes of ice being stored, and then also just like year over year dynamics. They move a lot, but like, for instance, I still talking about 50 centimeters a year for this Wasatch Rock Glacier, whereas I was just in Alaska, in Southeast Alaska, on the Mendenhall Glacier, and they were saying it moves like 1 to 2 meters per day. So like the whole glacier will turn over in 100 years. We have a chunk of ice from the White Pine Rock Glacier that we have been trying to manage to get it dated for a long time. We know it is older than using tritium, which is a way to date water. We know it's more than 70 years old, but we don't know how old it is. And I really would love to know how old the water is. In that same paper I was just talking about from the U recently, which I wasn't involved with, they noted the water coming out of Big Cottonwood Canyon was older than they expected. And I think part of that story is the rock glaciers in the canyon. So, yeah.
Question about tipping points and if there's any study going on to assess at what temperature you might see really rapid melting of rock glaciers.
Yeah, there isn't anything going on that I'm aware of. I mean, we're tracking trends of many of them. We're still tracking the ones in the Tetons, and we're also adding the Wasatch now. I mean, one of our first questions is, if we saw this pattern in the Teton range, is it also true in a different geologic setting a bit more south? Essentially, how far can we push that, going south? So we're encouraged by it, but we don't know for sure. But when the tipping point would occur of a rock glacier, actually the net insulating aspect not being able to keep up with warming, or the dynamics of avalanches, and if there's more rain and not as much snow that can then be avalanched, not sure yet. This is all it's exciting because it's new research, but it's also challenging because we don't have like the answers yet. Although we have one new answer, which is really cool. So we are making progress. But it's a good question. Doug.
I'm curious if you could provide an estimation for how much of the water that we drink here in Salt Lake Valley might have at one point been in a rock glacier.
That's a really good question. I can't yet. I can, for some of the higher elevation places, like there have been some studies. There's been one study using isotopes that estimated that about 30% of the water coming out of the LaSalle Mountains in summer was from a rock glacier in southern Utah. And judging by there's a rock glacier feeding the reservoir at Twin Lakes Pass, that is the water supply that goes into Brighton Township. Judging by the fact that the inflow to the lake was basically equal to the outflow of the lake last year, we think that lake is largely supported by a rock glacier in late summer. And so you can start to scale that up to how much water is coming out of the exit of Big Cottonwood Canyon. Something I would love to do is go out and get at least point estimates of flow measurements all along the rock glacier streams we know about, and then just compare that to the water data that, there's a lot of really robust water data outside of the kind of highest elevations. And so if we can fill in our side, then we can actually, use the data that already exists to make that kind of exact things. It'd be great to have that kind of stat just in talks like this also to help put it in context of the importance. Or if it's a lack of importance, that's also okay. That's part of science.
If you're a hiker and you're hiking around these, are you able to, over here, are you able to tell if that's a rock glacier or not if you're hiking by it? How do you tell?
Yes, totally. So you look for the front. You kind of look for that lobe-like place. If you can get above it, it's much easier to see. Like if you hike to White Pine Lake now, when you turn the last corner, you can see the rock glacier, and you will know exactly what I'm talking about the next time you're up there. So they're very obvious if you know where to look. And we can actually also tell if they're active and if they still have ice inside of them that's moving them around, because sometimes you'll see a very obvious rock glacier lobe with like trees growing on it. Trees are not going to grow in a place that's moving 50 centimeters a year. So if you look at the upper part of this thing, I mean, there's barely any plants because these rocks are, rolling over and tumbling down the mountainside. So yeah, you can certainly spot them. Yeah. Go see one. That'll make me really happy.
Okay, thank you, Scott. That's the end of the questions, and we'll head up to lunch.
Cool. Thanks, everyone.